Hey, welcome to Lab 2, Charge Tapes Revisited by me. So the purpose of this lab was essentially the same purpose as the first lab. We're trying to figure out the excess charge on a piece of tape by using another piece of tape to float it. However, this time we were trying to determine that computationally more accurately by enhancing our model of a piece of tape from a point charge to a line to a series, like a line of point charges. So here are our results from our experimental model in our last lab. This is what we determined by doing the experiment itself. And to kind of come up with this, we use some of these fundamental principles. Experimentally, we use Newton's second law, F equals ma, to compare the forces of gravity versus the forces working up. And because we know when it's floating, those are equal to each other. And then to calculate charges, we use Coulomb's law and all the derivations from that. But yeah, that's how we know the forces of electrostatics. Moving on to our computational model, we started using dq and de to break up our line charge into a series of small point charges, and then compute those discrete point charges individually and summate those charges in order to find the charge of a whole line of those charges, which is in effect a piece of tape. Oops, that's the wrong way. So our system is the top piece of charge tape. Our surroundings are the bottom piece of tape and the force of gravity. Here you can look at our initial conditions if you want to. That's how we set the experiment up. Here's a video of the experiment. As you can see, very cool. We get the tape to float up in the air before eventually I've pretty much discharged all the charge off my piece of tape on my hands. But we did get it to float, and so we know that we had enough charge on that to make it float. So where the force of electricity, the electrostatic force was equal to the gravitational force. So when we were calculating our observed force, it's not a super hard calculation. We first calculated the force of gravity by doing mass times the acceleration due to gravity in the y direction. We found that it was 0.00196 newtons. In the negative y hat direction, and we know thus if the tape was floating, the electrostatic force must be the same thing in the positive y hat direction. From there, we backtracked to the charge of the tape being equal to 1.5 times 10 to the negative 8 coulombs by going force of electricity, electric charge to Q in that equation. Number of electrons, we did the charge of the tape divided by the charge of an electron, got the number of electrons, and that ratio there was pretty simple. So here's the interesting stuff. So new computational model, it differs because now we have E field is the same thing as it was before. But now we have this line charge that makes, instead of one point charge, we get a line of those point charges. We make two of those lines, which are our two pieces of tape. And we compare them using our dq and de calculations we've been doing in lecture the past 2 weeks. And now we compare charges using those, which is a more accurate way of calculating that of those charges and those forces. So you can see we have a for loop that iterates for every discrete charge on the top, and it's a nested for loop with another one that goes through every charge on the bottom, and it calculates the force on each at each position. So here are our results. You can see at the end here, because at this end one here, we got this one pushing up, we got this one, this one, and towards the end, they're pushing very sideways, so we get this noticeable outward tilt. Where in the middle here, we have this one's pushing up, this one's pushing this way, but this one's pushing this way, and that kind of cancels out. We only get this up direction. And here you can see, we found our number of electrons to be slightly fewer than we found in the observational model. We found the number, and that affected our ratios, as you can see there, because our charge was lower, number of electrons was lower. Also disregard the negative sign on that. Some of our assumptions were that air resistance is negligible. Tape is not a point charge, but tape is a series of discrete point charges. which is a important difference. And the errors are, of course, we lose electrons to our hands in an uneven polarization of the tape. So if we'd modeled the tape as point charges, we would have expected more excess electrons per piece of tape. Our new model is more accurate because it's, a piece of tape is not just one electron, it's a series of them. So the more electrons we have in our computational model, the more true to life it is, so the more accurate our model is. All right, thank you.